Hi Bobcats. In this video we're going to take a look at something known as the quantum model of the atom. This is really one of my favorite chapters. Some of the things we'll start with in this video are taking a look at how light interacts with matter and how we can use that to learn something about the matter. We're going to describe light both in terms of being a wave and of being a particle that we call a photon, and we'll do a little bit of math with wavelength, frequency, and energy. If you take light and you pass it through a prism to spread it out into all of the component colors that make it up, we would expect for white light to get a complete rainbow, every color of the rainbow showing. But there are certain circumstances where you get what's called a line spectrum. You only get certain lines. One of those cases is shown over here on the right side. This neon light that says coffee and has the cup of coffee associated with it is what we call, or gives what we call an emission spectrum, which is shown over here, some examples. Emission spectra are created when atoms give off light. It wasn't real clear in the late 1800s as to why something like a neon light would only give off certain colors. Why is it only giving off these particular colors and not all colors at the same time? The opposite of this emission spectrum is over here on the right-hand side, and it's what we call an absorption spectrum. Where you are seeing the black lines is where light is being absorbed by a species. And again, this species isn't absorbing every color, it's only absorbing certain colors. And so things like these emission and absorption spectra were puzzles to scientists around 1900, or actually even by the mid-1800s. And so we were trying to figure out just why is this? Why do we get just certain lines and not all colors in these circumstances? Well, if we're going to figure out how light interacts with matter, we need to have a pretty decent description of light to work with. Sometimes light behaves as if it's a wave, and when it behaves as a wave, we'll characterize it in terms of things like wavelength and frequency. The symbol that we're going to use for wavelength is the Greek letter lambda, the lowercase version, and the symbol that we'll use for frequency is the lowercase Greek letter nu. Now, that's what the computer font for the Greek alphabet gives for nu. When I write this by hand, I tend to write a nu with a straight line and then a curvy line with a tail. So that way I distinguish it from the letter V in my own handwriting. Sometimes light acts as if it's a particle, and when it behaves that way, we're going to call it a photon, and we'll talk about the energy, E, that's associated with that photon. And what's really cool about this wave-particle duality is that the behavior that we observe for light depends entirely on how we set up the experiment to observe it. If we set it up to observe wave properties, we observe wave properties. If we set it up to observe particle properties, we observe particle properties. So neither one of those descriptions is quite complete. We need both of these things in order to fully describe light. Light is simply a small part of what we call the electromagnetic spectrum. Over here in this graph, we have right here in the middle where you see this rainbow, the portion of light or the portion of the electromagnetic spectrum that's known as visible light. And really it's pretty much defined by what our eyeballs can see. Let's see, the wavelengths are given up above, and the frequency and energy are shown down below. So the low frequency and low energy side is over here towards the left. We end up with things like radio waves and microwaves, infrared radiation, ultraviolet X-rays, and gamma rays going from low energy to high energy. and that all of those things together make up the electromagnetic spectrum. Different portions of the spectrum give us different information about matter. For instance, if we look at how microwaves interact with light, we get information about how molecules rotate or tumble. And from that data, we can determine things like the bond lengths between two atoms based on something called the moment of inertia. If we look at the infrared portion, we can get information about what atom is bonded to another atom, because at this point we're looking at vibrations of those bonds. So yeah, in the infrared portion, we're looking at bond vibrations, and so that'll tell us things like, oh, in this molecule we have carbon bonded to oxygen and it's a single bond, whereas in this other molecule we have carbon bonded to oxygen and it's a double bond. If we look at the visible portion and on in to the UV, and this is usually done the other way around, they usually call it UV vis, we get information about electron energy levels. And if you go on up to higher energies with X-rays, you tend to get information about like crystal lattices and how atoms are put together in solids. This slide is summarizing the formulas that you will need for any sort of calculations we'll do with light. Let's see, so just to define a couple of things, if we go from one spot on a wave to the next corresponding spot, like here what I just marked off was trough to trough, that distance is known as the wavelength. So yeah, that's what we use lambda for. The speed of light is given by the constant c. I just realized I didn't put a numerical value in for this. We're going to use that c is 3 times 10 to the 8th meters per second. Let's see, the relationship here is that the speed of light is equal to its wavelength times its frequency. We can rearrange this equation a little bit. If you have the wavelength and you want the frequency would be equal to c divided by lambda. If you have the frequency and you want the wavelength, then the wavelength would be given by c divided by the frequency. If we want to determine what the energy of that light is, we're going to use this next equation, E is equal to h nu. If we have the wavelength instead, we can substitute c over lambda in for nu. And h is a constant known as Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. When I first saw this unit, I thought this was just plural of joules, but that's not it. It's actually joules times seconds for those units. As an example of the type of calculation you might do on light, let's calculate the energy of a photon that's emitted by the blue-green argon ion laser at a wavelength of 488 nanometers. Well, E, the energy of that photon, is equal to h nu. That would be great if I had the frequency, but I don't. I have the wavelength. So let's use the other form. E is equal to hc over lambda. Well, h was given as 6.626 times 10 to the negative 34 joules times seconds. C is 3 times 10 to the 8th meters per second. And then lambda is given as 488 nanometers. Okay, before I write in a unit here, joules, seconds, all of that, that's looking great. The seconds will cancel out with the divide by seconds, but notice I've got meters up top. I really need to get this wavelength into the base metric units, the base SI units. So instead of putting 488 nanometers, I need to write that in terms of meters. I think the easiest way to write this is to recognize that nano means 10 to the negative 9 and just substitute times 10 to the negative 9 in place of nano, and I still have meters. So now I just need to run all of this through my calculator, which I sat down to record this before I grabbed my calculator. All right, let's see if you already beat me through this calculation. We've got 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 488 times 10 to the negative 9. And my calculator is telling me that that is 4.07 times 10 to the negative 19. Now, in terms of units, seconds canceled out with divide by seconds, and meters in the top canceled out with meters in the bottom. So the only unit that I am left with now is joules. So 4.07 times 10 to the negative 19th joules. Also in this section, your textbook presents something called the photoelectric effect, which is something that Einstein was able to explain around 1903. And the cool thing about the photoelectric effect is that scientists discovered that if you took a metal sample and you bombarded it with light, sometimes when you did this, nothing would happen. But other times, depending on the frequency of the light, electrons might be ejected from the metal. And Einstein was able to explain this by saying, all right, let's look at these incoming photons, which are these purple arrows coming in here. And then the energy of that photon gets used up doing two things. One thing is symbolized here by the Greek letter phi, which stands for the work function for the metal. The work function simply is how much of that energy goes into simply knocking that electron out of the metal. And then the rest of that energy goes off as the kinetic energy of the electron. So however much energy is left from that photon beyond the work function just simply goes into the speed of the electron, because remember that kinetic energy is 1/2 mv squared. So scientists learn quite a bit about metals by looking at how they interact with different frequencies of light. So our objectives here were mainly to look at how we can learn things about matter from the ways that it interacts with light. And along the way, in order to explain some of that, we did need to talk about the wave-particle duality of light and how we characterize light both as a wave and a particle. And so we'll talk about wavelengths, frequencies, and energies for light.